Welcome to the second lesson on the scientific method. I'm Wendy Nofke, and I'm going to present this brief lecture for you here on the scientific method to give you a little bit more detail, picking up from last week. So Carl Sagan has a nice quote to get us started here. Science is a way of thinking more than it is a body of knowledge. And that pretty much conveys exactly what we are trying to get across with the scientific method, is that we want you to learn how to think and approach things in a scientific way. It's not as much about memorizing information, but learning to analyze and use the information that you're able to find. The goals of scientific investigation include examining new phenomena, gaining new knowledge, and building on our current understanding. The scientific method is a tool that we use. It's our guide to solve these problems. It helps us initiate the investigations and describe the way science works. First, we start out with the hypothesis. The hypothesis is the suggested explanation of a question or a problem. There's two requirements that a hypothesis has. It must be testable and it must be falsifiable. We must be able to identify when our hypothesis is actually false. We've got a few general steps that are involved with the scientific method. First is to make observations. This helps us to prevent wasting our time as much with the steps that we take in the future. That way we only actually do the experiments on things that we are likely to actually get a good result on. We're not going to be repeating things that we already can find in other ways or things that have already been tested. Next, we ask questions. We need to know what exactly we are looking for and to make sure everyone is on the same page on what we are seeking out in the process. The next step is constructing the hypothesis, where we take those questions and our previous observations into consideration. Finally, we will test the hypothesis with experiments. And this is usually what most people will think of when they think of science, is just conducting the experiments, even though quite a bit goes into it beforehand. After we conduct the experiments, we're going to look at the data and draw conclusions. Sometimes your experiments will give you the answers you need right away, but most of the time they're going to need to be revised and repeated. Finally, we will communicate the results. This allows various researchers to work together and people from different fields to collaborate on the information that you find in your scientific experiment. So when we develop this hypothesis, we want to use prior evidence and knowledge. When we know something is already in existence, we don't necessarily need to retest it, and this will make our process more efficient. We also want to make sure that we can come up with a definite false answer in there, a way to prove that the hypothesis is false. There are multiple parts of our experiment. The controls are going to eliminate and help limit the variables that are affecting the outcome. If we're looking at doing an experiment and there's several different things going on at the same time, it's going to be hard to establish cause and effect, or exactly what variable is influencing the changes that we're observing. The variables are the factors that can change over the course of the experiment. A variable must be tested and measured accurately to avoid and minimize experimental error. One of the goals is to make sure your experiment is reproducible. This allows other experimenters and scientists to go through and verify your work, and helps to control things being published that shouldn't be in the future, and us to have a false understanding of things. With controlled variables, all the variables are kept constant to prevent them from influencing the result. An example would be if you're testing something on humans and you want to test a diet, and you want to see, does this diet cause the humans to gain weight or to lose weight? If you just give them the product and send them home, there's numerous other variables that can influence that. You can have some of the participants in your study overeat. You could have some of the participants undereat. Some of the participants may exercise a lot, and some may be completely sedentary. With all those other variables, there would be no way of firmly saying, we know that what we gave them, our product, is actually what caused the change. So by controlling those variables and having everyone eat the same thing, having everyone do the same activities, we've controlled the variables and get a better result. So this leads us to creating a control group and an experimental group. By having a control group, you can look at the change your experimental group makes from the ordinary situation. You can look and see what would normally happen in the scenario, and then what happens when you actually do your experimental manipulation or treatment. So the control group will be the one that does not receive the experimental manipulation or treatment. The experimental group will receive the manipulation or treatment that's being evaluated. Our variables are also going to be different. The independent variable is also known as the manipulated variable. This is going to be the factor that's controlled by the experimenter to determine the relationship to the observed phenomena. The dependent variable, or the responding variable, is going to be what changes in response to the manipulated or independent variable. So we will actually control the independent variable or the manipulated variable. We will do something different with that, and then we're looking to see what happens with the dependent or responding variable. So in that example that we looked at previously with the diet, the independent or manipulated variable would be the substance we give those people for weight loss. The dependent or responding variable would be their actual weight loss in the situation. How much did their weight change? Having blinds in an experiment can also help. With a controlled experiment, you're going to have two identical experiments carried out, with the only difference being the manipulated and the independent variable. So in our example with the weight loss product, you would have one group that's going to get the weight loss product and one group that is not going to get the weight loss product, but everything else they're going to do is the same. By having a double blind, neither the experimenter nor the participant knows which group they're in. And in most cases, to do a double blind, we need to have a placebo, which is a false test or substance given to the control group. This is helpful in minimizing preconceptions in there, so that the person isn't just going to have a positive result because they're expecting it. So in our weight loss experiment, we would have one group that would take our weight loss substance, and then we would have our control group take a placebo or a false pill in there, so that they don't know which group they are in, and it's going to take out the fact whether or not they're just losing weight because they are expecting to lose weight in this experiment. Sometimes we can't actually perform experiments. Sometimes there may be some ethical concerns in performing them, so we have to observe the results retroactively. These are natural experiments. With these, it's more difficult to determine the result if it's due to correlation or if it's due to causation. So correlation is going to be if we just see two pieces of data occurring together or two statistics changing together, it doesn't necessarily mean one has caused the other. With the ethical concerns, sometimes it is simple as things are good or bad, right or wrong. Other times there's going to be a lot more gray area in here, where there can be panels that will be put together to evaluate and determine should these studies be done or should they not be done. It's just weighing the cost versus the risk. What is going to be the benefit to society? What is the risk to society in doing these experiments? When doing your experiment, you want to reduce error as much as possible. Accuracy is a measure of how close the calculated or measured value is to the actual value. Precision is the ability to reproduce or repeat and get the same results. In an experiment, you want to try and be both as accurate and precise as possible. Sometimes you're going to be limited by your equipment or your experience, And it's always best to note those things and acknowledge those things when you do your write-up. Some sources of error can be equipment malfunctioning, user inexperience, incorrect use of equipment, or not having proper equipment. Finally, we look to interpret the results. And hopefully we always get some sort of results in there, but there are cases where you have a null hypothesis, that there is no relationship between the independent and dependent or manipulated and responding variables. Oftentimes we will be looking or expecting to get a result, and that can be a dangerous thing in science. If you have a null hypothesis, it's just a null hypothesis that needs to be acknowledged in the scenario. We don't want to have a scientist looking too hard to get results and then falsifying the results in the long run. That's one of the reasons for having such good documentation with scientific experiments and having them be repeatable, is that another researcher can go along and say, you know what, I was hoping the result would be negative, and seeing if they still get the same result, if there's any influence of the actual experimenter in there. Ideally, we want to minimize that influence as much as possible. Something that's often used in interpretation is something called Occam's razor, which states that the explanation should involve as few assumptions as possible. We want to use the data that we do have, but we don't want to jump to conclusions with information that we don't have. Scientific research has become very interdisciplinary these days. Clear and accurate communication is essential. So we may have somebody who is specializing in statistics looking at information. You may have somebody that works in information technology helping to gather the information and process it in a computer. You could have a biologist working on conducting an experiment in there. You could have a chemist who's looking at things on a chemical level, all working together to come up with information and research and interpreting the research. Every once in a while you can have a superseded theory, a theory that was once commonly accepted but no longer considered the most accurate or complete description by mainstream science. So we see these actually occur all the time in health occupations. One that is fairly recent is it used to be thought that we wanted to try and get calcium supplementation levels fairly high. New research has actually come along and superseded that, indicating that people are better off to have their calcium supplementation be a little bit more moderate in there and to actually account for what they eat in their diet. Some of the big things that have been superseded through time is probably that the Earth was flat, and determining that it is actually round. But we still see this happen all the time with new research. By involving multiple disciplines, you can often put new insights into your work, and the analysis of the information can be a lot more beneficial to society overall if you have more eyes looking at it. Thank you.